All right. Welcome everyone. Snow day today, so we're going to do a lesson online, going back to 2020 a little bit here, I guess. Um, so today we're going to start our first kind of investigation into the relationship between various properties of a gas and see how they relate to each other. Specifically today, we're going to look at the relationship between the number of moles of a gas and its volume. So we're going to go through you are going to do a activity using the PhET simulation. You're going to fill out this worksheet here. And then you are going, as part of this activity, you're going to create a graph that you will either submit to OneNote as a separate file, or you could paste it to the bottom of this page and then submit all of it. That is this worksheet and your graph all together. But you could also, again, like I said, submit the graph separately. Canvas will let you submit 2 different files for this assignment. So once you're done with this classwork, for homework, what you want to do is complete some of these practice activities based on an equation that you will derive upon completion of this worksheet. So let's talk about this worksheet a little bit here. So the first thing you want to do, obviously, is kind of just follow through with these directions on the worksheet. So in order to do that, let's go ahead and open up the PhET simulation. So you are going to select this box over here, gas laws. It's similar to what we did last time, or well, maybe you use this specific version of it instead of the intro, but this allows you to control several things. And what we want to do here, the first thing I do is I just close the box to its minimum size or width. And then I put in some particles. You can pick whichever particles you want. You can pick the blue ones or the red ones. It doesn't matter. And I'm going to put some in there. And then what we are trying to investigate here is the relationship between the volume of this container versus the number of particles. What that means is that we have to keep 2 things constant. Well, the other measurables for a gas would be the pressure and the temperature. And so we're never going to heat or cool the box, and we're never going to, well, the simulation will do this on its own, but it will never change the pressure. That's what you'll notice. And it does that again by selecting, it does that when we select this little button or toggle here. The other thing I want to do here is adjust be able to measure the width of the box. And so I'll go ahead and click that. One thing to note, all right, the volume of the box is what we really care about because, well, gases occupy a 3-dimensional space, so they occupy volume. But this is a measurement of length. And so if we go back to the worksheet really quick, what you see here on the directions is it kind of notes that, hey, the box has some dimensions in terms of depth and height. And you probably know that width times length times height is equal to the volume of a cube or any kind of like prism, I guess. And so what we want to do here is note that we have some numerical value for the width, but that width is multiplied by some dimensions a squared in order to get to the volume. So when you're running your numbers here, this is going to be the number of particles, and this column here is going to be the width that you see in the simulation. But that width is multiplied by a squared to give you a total volume in terms of nanometers cubed. Hopefully that makes sense. When you start this worksheet, once you put in some particles, you record the number of particles, you record the temperature, you record the initial pressure, and hopefully, when you're done getting all your data points, the temperature and the pressure has not changed. They shouldn't. Okay, so let's go ahead and go back to the simulation here. If I can find my window, sorry, using multiple windows here. Switch back to this. Oops. Hang on. Oh, lost my window. All right, there it is. Okay. So you're going to adjust the number of particles by pressing this button here. Do not do the bicycle pump, because if you do the bicycle pump, you insert too many particles and the box blows up. You don't want that to happen. And so you will put in a few particles at once, right? Depending how many you start with, that will impact how quickly the box expands. Again, what you want to avoid is something like this, where you get an error. If you get an error like this, you have to restart the simulation. So that's not a big deal. I'll go ahead and just put in, if you put in a lot in the beginning, then the pressure will be higher. And so the change as you insert particles won't be as dramatic, and that will allow you to kind of insert a little more at a time without blowing up the box. So you put in a few particles at a time, record the width, which again corresponds to a change in volume, until you fill out the table, right? So you can kind of play around with that. Once you're done with that, let's go back to our window here. Once you're done with that, what you want to do next is you are going to plot everything in Excel. So this is going to be your X column. This is going to be your Y column. And once you have your data copied and pasted over to Excel, let's take a look at how we might handle that data or generate a plot from it. Okay, so here's some some sample data. This doesn't correspond to any of the gas law data. This is just an illustrative example to show you how to plot stuff. So once you have your number of particles in your X column and the width of the box, which, well, technically the volume, on the y-axis, you're going to insert a scatter plot, and you'll get something that looks like that. All right. Your data should be hopefully linear, I think, right? If you think about it. And I'm going to just delete these grid lines. I actually never really like these grid lines. Okay, so a couple things you need here. You need a chart title, which should be descriptive as to what you're doing. My advice always is for students to imagine themselves creating a plot and then showing it to someone without any context. They should be able to read your title and figure out what it is. That is what you're plotting. You also need axes labels, and so to do that, you go to Add Chart Element, depending what version of Excel you have, but you should all have the same version. So you can add a horizontal and also a vertical axes title. And these axes titles should tell the audience the type of measurement and the units that are associated with that measurement. So, as an example, since your x-axis here was the number of particles, you would write number of particles, and then in parentheses, it would be the count or number. You can get this information actually from the worksheet. So let's go back and look at the worksheet just so that you're aware that the information's there. So if you look at the worksheet here, right, it gives you a type of measurement. So in this case here, it's the number of particles, and then the units are, well, just number, right, or count. The volume, right, that would be your y-axis, and this is the unit of measurement, a squared nanometers cubed. All right, so you've gone ahead and made your plot. What you want to do next is you want to insert a trend line, and to do that, you just hit your right mouse button, your right cursor button, and then you add trend line down here, and then a little window will pop up. The other thing you want to add to the plot, if you read the directions on the worksheet, is you want to display an equation, and you want to display an r-squared value. So go ahead and do that. And then pretty much done, right? Again, make sure you have a proper chart title that's descriptive of what you're doing, right? What are you plotting versus what? Proper axes titles with measurement and correct units. Okay, so I'll give you a moment to do that. I would pause the video here, and then once you have plotted all your data, we can kind of move on to the rest of the worksheet, which I will talk about. So pause here. All right, I assume that you have plotted your stuff, and you didn't just pretend to do that. So let's kind of take a look at the rest of the worksheet here. So in the rest of the worksheet here, you want to determine the relationship between the volume and the number of moles of particles in a system, and whether or not it's directly or inversely proportional. The other way of asking this question is, if you increase the number of moles, what happens to the volume of the box? Does it also increase? That is it a direct relationship, or is it an inverse relationship? An example of an inverse relationship would be where a variable, something is increasing, and then the thing that the other property would be decreasing. So that's an inverse relationship. But a direct relationship would be if one thing increases, the other property also increases. So you can kind of consider that. And then it has you write some equations for your relationship between moles and volume. The first equation you will just take off your plot, right? On your plot, you have a trend line where y equals some slope multiplied by x plus a y-intercept, right? That is, let me go ahead and write that here on the side, I suppose. Whoops. All right. So you have y equals mx plus b. In this case here, your b should be 0, right? Because if you have no particles, your volume should be 0. So in your graph, your slope will be some numerical value, but your intercept should be very close. Should be very close to 0. It might not be just because of some things in the simulation, but I would go ahead and just assume it's close enough to 0. So you're going to start with something like that, right? So again, even if your plot doesn't say that the y-intercept is 0, you can just set it to 0, because if you don't have any particles, well, logically your volume should be 0. So what you want to do here is, instead of writing your equation as y equals mx plus b, you want to kind of think about what is your y value and what is your x value on your plot, right? That is, what did you plot as x and what did you plot as y? Well, I'm hoping, right? I'm going to guide you a little bit here, but I'm hoping you realize that x is really the number of particles, right? That's what we plotted along the x-axis, and the y was the volume. And so we can kind of rewrite this equation. If we insert proper variables, we can write that as v, and our x can be number of particles, and in this case, we're going to give it the variable n, corresponding to number of moles. I know that you didn't plot moles of particles, but it's identical to what you did. So equation 2 is maybe a little bit less obvious to you as to how you might write it. But let's just kind of go through that, just kind of walk you through. So I'm going to write a plot here. So, well, here, let's do this. So rearranging the equation as we just kind of are inserting variables here. We have volume equals our slope, which instead of writing m, I'm going to write a constant, because the slope is a constant, right? I hope you all agree with that based on what you know about math. And this is going to be multiplied by some n. Now, if I rearrange this, right? If I rearrange everything and get the constant on one side, I hope you agree that you have an equation that looks like this. V over n is equal to some constant. All right. And again, this might be something that you write for equation 1. Well, sorry. This is how we might get to equation 2. So consider something with me really quick, right? So if we have the volume here, and the number of moles here, this is kind of what you plotted. You have some line. It should go through 0 technically, but drew it poorly. So let's say that this data point here is n1, and this is corresponding to some volume 1, right? And then we change some things, right? And we get to this point here. We have n2 and some other volume 2, right? These are 2 data points that we have on the same line. Now, What we know about the system is that on all those points, the pressure is the same as and the temperature is the same. We also know, based on the equation that we wrote above here, that the volume divided by N1, right? Volume 1 divided by N1 is equal to some constant. Specifically, that constant is the slope. Now, if we take, let's use a different color here. If we look at V1, V2, and we divide that by N2, well, that also equals a constant, right? Based on the equation, again, we derived above, and this is equal to the slope. But because these points sit on the same line, that is, because these data points were collected under the same pressure and the same temperature, we can rewrite a general equation where V1 over N1 equals V2 over N2, right? And this equation we can use to solve a lot of problems for different systems. And so let's draw a picture here. So let's say you have some system here, right? Some box. Let's just do a box. And actually this box is going to be a little piston here. Right? That is, it's free to change volume, right? And so if I put some particles in here, and this is some volume, right? This is some volume 1 and some number of particles 1, right? There's some count of particles in there and it has some volume. And this is at constant at some temperature and pressure. Well, if I take the same system and let's say I fill it up with more particles. So let's say this system has a valve here, right? And I can put in more particles. If I put in more particles, all right, let's just say I put one more in there, right? So this is some V2 and N2. These variables don't really correspond to above because, well, in this system here, V2 and V1 have different numbers of particles. This is at the same temperature and pressure, right, as this. Well, I know that the relationship between the number of particles and the number of moles in both these containers is given by the equation that we just wrote above, right? So I can use this to solve some problems. That is, if I don't know the volume right here, but I know if I know this, I know this, and I know this, well, I can solve for V2, right? One equation, one unknown, not a problem. So you're going to solve some of those style of problems down here for parts 12 and 13. So once you get this worksheet all done, you can go ahead and submit it to Canvas. And then there's a little homework assignment here to do some extra practice using that same equation that we kind of derived above. Oh, I guess I should note one more thing. This worksheet also has you think about the pre-lab that you completed last time and discussing how your data that you collected for this worksheet pertains to kinetic molecular theory. That is based on like what you know about collisions and pressure, right? Why does the box have to expand in order to maintain the same pressure? Right? That's what you kind of want to think about here. Remember that the particles are moving at the same speed because we're at the same temperature. So why does the volume need to expand in order to maintain the same pressure? Right? That's kind of the question that we're asking here. Okay. So that's all we got. I hope this video was helpful to kind of explain how to complete the classwork today. A tad on the longer side, but I hope it helped kind of walk you through some of the logic here. So please email us if you have any questions. Enjoy the snow, I guess, once you complete this worksheet. Take care. Don't forget to like, favorite, and subscribe to this YouTube channel if it was helpful. I'll see you next time.